Welcome to DAR Tutors for online and home tuition. Today, we will begin our exploration of measurement, a fundamental topic in IB mathematics, applications, and interpretation higher level. In this comprehensive chapter, we will cover four main areas: circles, surface area, volume, and capacity. We will build upon your existing knowledge and delve into more complex problem-solving techniques relevant to your IB syllabus. The goal is to equip you with the precise tools and understanding needed to excel in your examinations. Our first topic, Section A, covers circles, arcs, and sectors. By the end of this section, you will be able to calculate the arc length, area, and perimeter of sectors and apply these concepts to solve complex geometric problems. First, let's recall the fundamental formulas for a circle with radius r. The circumference, or the distance around the circle, is c equals 2 pi r. The area, or the space inside the circle, is a equals pi r squared. These are essential and should be committed to memory. An arc is simply a part of the circumference of a circle. We can measure its length using the angle it subtends at the center, which we'll call theta. The formula for arc length is theta divided by 360 degrees, all multiplied by the circumference of the circle, 2 pi er. The fraction theta over 360 tells us what proportion of the entire circle the arc represents. Similarly, a sector is a part of the area of a circle. You can think of it like a slice of pizza. Its area is calculated using a similar proportion. Theta divided by 360 degrees multiplied by the circle's total area, pi r squared. This gives you the area of that specific slice. Finally, let's consider the perimeter of a sector. Remember that perimeter is the total distance around the shape. The perimeter of a sector is composed of the arc length plus the two radii that form its straight sides. So, the formula is 2r plus the arc length, or 2r plus theta over 360 times 2 pi r. It's the two straight edges plus the curve. Now let's work through some examples to solidify these concepts. Consider a sector with a radius of 3 centimeters and a central angle of 48 degrees. We need to find its arc length, perimeter, and area. First, for the arc length. Using the formula arc length equals theta over 360 times 2 pi r, we substitute the values. Theta is 48, r is 3. This gives us 48 over 360 times 2 pi times 3. Calculating this, we find the arc length is approximately 2.51 centimeters. This is how long the curved part of our sector is. Next, let's find the perimeter. The perimeter is 2 radii plus the arc length. So we have 2 times 3 plus the arc length we just found, 2.51. This results in a perimeter of approximately 8.51 centimeters. The total distance around our shape is about 8.5 centimeters. Finally, for the area of the sector. Using the formula area equals theta over 360 times pi r squared, we substitute the values. Theta is 48 and r is 3. This gives us 48 over 360 times pi times 3 squared. The calculation yields an area of approximately 3.77 square centimeters. This represents the space enclosed by the sector. Let's tackle a more challenging problem from your textbook, question number 9. The problem describes a lampshade that is a segment of an annulus, a ring shape. It has an area of 0.32 square meters, a shorter arc of 1 meter, and a slant height, or width, of 28 centimeters. We're told to model the lampshade as the area between two sectors with a common angle theta, and radii r for the inner arc and capital R for the outer arc. The first step is to establish the dimensions. We have an inner radius r, and the slant height is 28 centimeters, which we must convert to meters, so 0.28 meters. This means the outer radius, capital R, must be r plus 0.28. It's the inner radius extended by the width of the lampshade. This relationship is key to solving the problem. First, let's use the shorter arc length. The formula for the inner arc is theta over 360 times 2 pr. We know this equals 1 meter. This gives us our first equation relating r and theta. Next, let's use the given area. The lampshade's area is the area of the larger sector minus the area of the smaller sector. The larger sector has radius r, which is r plus 0.28. The smaller sector has radius r, so the area is theta over 360 times pi times the quantity r plus 0.28 squared minus theta over 360 times pr squared. We can factor this to get theta over 360 times pi times the difference of squares. R squared minus r squared equals 0.32. This simplifies to 0.32 equals theta over 360 times pi times the sum of the radii r plus r times their difference r minus r. This is a very useful simplification. Now we substitute our known values. R minus r is 0.28 and r plus r is t4 plus 0.28. This results in the area equation 0.32 equals theta over 360 pi times 0.28 times the quantity 2r plus 0.28. This should look familiar from the textbook. It's the expression they asked us to show in Part A. Now that we have our two main equations, let's solve for r and theta. Here are our two equations, one from the inner arc length and one from the total area. From our first equation, we can isolate theta over 360. It equals 1 over 2 pr. This expression represents the fraction of the circle that forms our sector. Now we substitute this expression for theta over 360 into our second equation. This eliminates theta, leaving us with an equation containing only r. We get 1 over 2 pi I r times pi EC times 0.28 times the quantity 2r plus 0.28 equals 0.32. We can simplify this. The pi in the numerator and denominator cancel out. So we have 1 over 2r times 0.28 times the quantity 2r plus 0.28 equals 0.32. Let's expand the left side. 0.28 over 2r times 2r is just 0.2, and 0.28 over 2r times 0.28 is 0.0784 over r. So we have 0.28 plus 0.0784 over r equals 0.32. Now we solve for r. Subtract 0.28 from both sides to get 0.0784 over r equals 0.04. Rearranging gives r equals 0.0784 divided by 0.04, which is exactly 1.96 meters. So the radius of the smaller arc is 1.96 meters. With r, we can find the outer radius, capital R. It's r plus 0.28, so 1.96 plus 0.28, which is 2.24 meters. Finally, we can find the angle theta using equation 1. Plugging our value for r into the equation for theta over 360, we get 1 over 2p times 1.96, which is 1 over 3.92p. Multiplying by 360 gives theta equals 360 divided by 3.92p, which is approximately 29.28 degrees. This is the angle of our sector. For the last part, we need to find the length of the longer arc. This is the arc of the outer sector. Its length is theta over 360 times 2p times the outer radius r. Using our calculated values, we get 1 over 3.92 pa times 2 pi times 2.24, which simplifies to 4.48 over 3.92 or 1.14 meters. Now we move to section B, surface area. The objective here is to learn how to calculate the surface area of various three-dimensional solids, starting with those that have flat or plane faces. The surface area of a solid is simply the sum of the areas of all its faces. A plane face is a flat, two-dimensional surface. To find the total surface area, we calculate the area of each individual face and add them all together. A helpful way to visualize this is to imagine the solid's net. A net is a two-dimensional pattern you can cut and fold to form the solid. For any prism or pyramid, finding the total area of its net will give you the total surface area of the solid. Let's apply this to a square-based pyramid, as shown in example 2. We have a square-based pyramid with a base side length of 13.2 centimeters and a vertical height of 10.8 centimeters. Our task is to find its total surface area. The net of this pyramid consists of a square base and 4 identical triangular faces. To find the total surface area, we must find the area of the base and the area of one triangle and then sum them up. The base is a square with side 13.2 centimeters. Its area is simply 13.2 squared, which is 174.24 square centimeters. Now for the triangular faces. Each is an isosceles triangle with a base of 13.2 centimeters. To find its area, we need its height, which we'll call h. This height is often called the slant height of the pyramid. To find the slant height, we need to use a key visualization. Imagine a right-angled triangle inside the pyramid. Its vertices are the apex, the center of the base, and the midpoint of one of the base edges. The vertical height of the pyramid is 10.8 centimeters, and the horizontal distance from the center to the midpoint of the base edge is half of the base side, which is 6.6 centimeters. The hypotenuse of this triangle is the slant height we need. Using the Pythagorean theorem, h squared equals 10.8 squared plus 6.6 squared. This gives h squared equals 116.64 plus 43.56, which sums to 162. So, the slant height h is the square root of 160.2, which is approximately 12.6 centimeters. Now we have the height of each triangular face. The area of one triangle is 1/2 times its base, 13.2 times its height, 12.66. This is about 83.56 square centimeters. Finally, we sum the areas of all the faces. The total surface area is the area of the base, 174.24, plus 4 times the area of one triangle. That's 174.24 plus 4 times 83.56, which equals 174.24 plus 334.24. This gives a total surface area of approximately 508.48 square centimeters, which rounds to 508 square centimeters to 3 significant figures. Let's move on to solids with curved surfaces such as cylinders, spheres, and cones. By the end of this scene, you will be able to apply the formulas for the surface area of these shapes to various problems. These objects, like a cylinder or a sphere, have curved surfaces, but we can still calculate their area using specific formulas. These are derived from more advanced calculus, but for IB you need to know and be able to apply them. First, the surface area of a cylinder with radius r and height h. It consists of 2 flat circular ends, each with area pr squared and a curved side. Imagine unrolling the curved side. It forms a rectangle. Its width is the circumference, 2 pi r, and its height is h. So its area is 2 pi r h. Adding these together, the total surface area is 2 pi r squared plus 2 pi r h. Next, for a sphere with radius r, the surface area is given by the formula A equals 4 pi r squared. There's only one curved surface, and this formula covers its entire area. This is a compact and very important formula to remember. Finally, for a cone with radius r and slant height s, its surface area is made of a flat circular base with area pir squared and a curved side. Imagine unrolling the curved side. It forms a sector of a circle. Its area is pi rs. So, the total surface area is pi r squared plus pi rs. Let's apply these new formulas with example 3 from your notes. The example asks us to find the surface area of 3 different solids, each with a slight variation that requires careful application of the formulas. Part A asks for the surface area of a cylinder with radius 6 centimeters and in height 15 centimeters, which is hollow on top and bottom. Because it's hollow, we don't include the area of the circular ends. We only need the curved surface area. The formula for the curved surface is 2πrh. Plugging in our values, we get 2 times pi times 6 times 15. This calculates to 180 pi, which is approximately 565.5 square centimeters. So, the area of the side of this cylinder is about 565.5 centimeters squared. Part B asks for the surface area of a sphere with a radius of 8 centimeters. This is a direct application of our formula for a sphere. The formula is 4 pi r squared. Substituting r equals 8, we get 4 times pi times 8 squared. That's 4 times 64 pi, which is 256 pi, or approximately 804.2 square centimeters. Part C asks for the surface area of a cone with a base radius of 5 centimeters and a slant height of 12 centimeters. This is also a direct application of the cone formula. The total surface area is PR squared plus pi rs. Substituting our values, we get pi times 5 squared plus pi times 5 times 12. This is 25 pi plus 60 pi, for a total of 85 pi, or approximately 267.0 square centimeters. Let's explore a fascinating investigation into the surface area of a sphere, following the spirit of Archimedes. This investigation helps us understand why the formula A equals 4pr squared is true. This type of inquiry is excellent preparation for your IB internal assessment. Archimedes proposed a beautiful idea. He imagined a sphere perfectly inscribed within a cylinder. This means the cylinder has the same radius r as the sphere, and its height is twice the sphere's radius, or 2y. The first part of the investigation asks us to find the area of the curved surface of this cylinder. Remember our cylinder surface area formula, 2prh. For this cylinder, the radius is r and the height is 2r. So the curved surface area is 2 pi r times 2r, which simplifies to 4pr squared. This is a very significant result. Now here's the magic part of Archimedes' argument. He showed that if you take any thin horizontal slice, at any height y, its contribution to the sphere's surface area is exactly the same as its contribution to the cylinder's curved surface area. For a slice of thickness delta y on the cylinder, the area is simply the circumference 2pr times the thickness delta y. Let's try to verify this for the sphere. Consider a slice of the sphere. Its radius, x, changes depending on the height. The surface area of this slice can be approximated by its circumference, 2πx, times the length of the curved edge of the slice, delta s. This delta s is related to delta y by similar triangles inside the sphere's cross-section. This similar triangles argument shows that the circumference 2πx multiplied by delta s is exactly equal to 2 pi r multiplied by delta y. So we've shown that the surface area contribution from any slice of the sphere, 2 pi r delta y, is the same as the contribution from the corresponding slice of the cylinder. If you add up all these infinitesimally thin slices, you find that the total surface area of the sphere is equal to the total curved surface area of the cylinder that contains it. Hence, the surface area of a sphere is 4 pi r squared. It's time for our call to action. If you're finding these concepts helpful and want to go deeper, Dart Tutors offers expert personalized tuition in IB, A-Level, and IGCSE curricula. Our experienced tutors can provide the support you need to build confidence and achieve your academic goals. Whether you need help with specific topics, exam preparation, or want to master the full syllabus, we are here for you. Visit dartutors.com to learn more and book a free introductory session. That's dartutors.com. Unlock your potential with Dart Tutors. Now let's continue with our lesson on measurement. We now turn to Section C. Volume. Volume is a measure of the three-dimensional space a solid object occupies. The objective is to calculate the volume of various solids, including prisms, pyramids, cones, and spheres. Let's start with solids of uniform cross-section, like prisms and cylinders. A solid of uniform cross-section is one where any slice parallel to the base will be identical in size and shape. Think of a loaf of bread, where every slice is the same. For any such solid, the volume is found by multiplying the area of one of these cross-sections by the length or height of the solid. For a simple cuboid or rectangular prism, the cross-section is a rectangle. Its area is length times width. So the volume is length times width times height. For a cylinder, the cross-section is a circle with area PR squared. Multiplying by the height h gives the volume PR squared h. These are the fundamental volume formulas for prisms and cylinders. Let's work through an example of a triangular prism, which is a solid of uniform cross-section. Consider a prism with an isosceles triangular base with sides 10 centimeters, 10 centimeters, and 12 centimeters, and a length of 30 centimeters. We need to find its volume. To find the volume, we need two things: the area of the triangular cross-section and the length of the prism. The length is given as 30 centimeters. First, let's find the area of the triangle. To use the formula 1/2 base times height, we need the height of the triangle. We can find this height using the Pythagorean theorem. An isosceles triangle's height bisects its base, creating two right-angled triangles with a base of 6 centimeters and a hypotenuse of 10 centimeters. So h squared plus 6 squared equals 10 squared. H squared equals 100 minus 36, which is 64. Taking the square root, we find the height h is 8 centimeters. Now we can find the area of the triangular cross-section. It's 1/2 times the full base of 12 centimeters times the height we just found, 8 centimeters. This gives an area of 48 square centimeters. Now that we have the cross-sectional area, the rest is straightforward. The volume is the cross-sectional area times the length of the prism. That's 48 square centimeters times 30 centimeters, which equals 1440 cubic centimeters. This is the amount of space occupied by the entire prism. Let's work through another problem from exercise 6C1, question 1C. This one involves a prism with a trapezoidal cross-section. The problem asks us to find the volume of this prism. Notice that the front face is a trapezoid. We can see that the parallel sides of the trapezoid are the vertical edges, which are 8.6 centimeters and 13.8 centimeters long. The distance between these parallel sides is the width, which is 12.9 centimeters. This width is the height of the trapezoid. The length of the prism going into the page is 10 centimeters. For our trapezoidal cross-section, the two parallel sides, A and B, are 8.6 and 13.8 cm. The height, h, of the trapezoid is 12.9 cm. Now let's find the area of this trapezoidal cross-section. The formula for the area of a trapezoid is 1/2 times the sum of the parallel sides, times the height. Substituting our values, we get 1/2 times 8.6 plus 13.8, all times 12.9. That's 1/2 times 22.4 times 12.9. This gives us a cross-sectional area of 144.48 square centimeters. Now that we have the cross-sectional area, calculating the volume is straightforward. The volume of any prism is the area of its cross-section multiplied by its length. We multiply our cross-sectional area, 144.48, by the prism's length, 10 centimeters. This gives us a total volume of 1444.8 cubic centimeters. Remember, the key is to correctly identify and calculate the area of the uniform cross-section. Now let's consider a composite solid. Exercise 6C2, question 2C, provides an excellent example of this. The problem asks us to find the volume of a solid composed of a cone on top of a hemisphere. The hemisphere has a radius of 5 centimeters, and the cone has the same base radius of 5 centimeters and a height of 9 centimeters. To find the volume of a composite solid, we simply find the volume of each individual part and add them together. In this case, we need the volume of the cone and the volume of the hemisphere. First, let's calculate the volume of the conical section. The formula for the volume of a cone is 1/3 pi r squared h. Substituting the given values, we get 1/3 pi times 5 squared times 9. This simplifies to 1/3 pi times 5 times 9, which is 75 pi cubic centimeters. Next, let's calculate the volume of the hemispherical section. The formula for the volume of a sphere is 4/3 pi r cubed. Since we have a hemisphere, we take half of this. So the formula is 2/3 pi r cubed. Substituting the radius of 5 centimeters, we get 2/3 pi times 5 cubed. That's 2/3 pi times 1/5, which gives us 250 over 3 pi cubic centimeters. Now the final step is to combine these two volumes. The total volume is the sum of the cone's volume and the hemisphere's volume. That's 75 pi plus 250 over 3 pi. To add these, we need a common denominator. 75 pi is the same as 225 pi over 3. Adding the fractions, we get 225 pi plus 250 pi all over 3, which equals 475 pi over 3 cubic centimeters. If the question asks for a numerical value, we can approximate this to 3 significant figures. 475 pi divided by 3 is approximately 497 cubic centimeters. The process of breaking down composite solids into simpler shapes is a key IB skill. Our final topic in this video is capacity. You will often see the terms volume and capacity used interchangeably in everyday language. But in mathematics and science, there is a clear distinction. Volume is the amount of three-dimensional space that an object occupies. It is a property of the object itself. Capacity, on the other hand, is the quantity of fluid or substance that a container is capable of holding. It is a property of the container. So, a jug has a volume, but its capacity is the amount of water that can fit inside. The units for volume and capacity are closely linked. This is a crucial relationship to memorize. 1 cubic centimeter is equivalent to 1 milliliter. 1 cubic meter is equivalent to 1 kiloliter. Knowing this equivalence is essential for solving problems involving capacity. Let's look at a simple example to see this in practice. Example 8 asks for the capacity of a rectangular tank. We are given its dimensions, 2.6 meters by 3.19 by 1.45 meters. To find the capacity, we first need to find the volume of the tank in cubic meters. The tank is a cuboid, so its volume is length times width times height. We multiply the three dimensions together, 2.6 times 3.1 times 1.45. This gives a volume of 11.687 cubic meters. Now we use our conversion factor to find the capacity. Since 1 cubic meter is equivalent to 1 kiloliter, the capacity of the tank is 11.687 kiloliters. This means the tank can hold 11,687 liters of fluid. Understanding this distinction and the conversions is vital for many practical problems. Let's work through a practical problem involving capacity and volume from example 9. The problem states that 17.3 millimeters of rain falls on a shed roof with dimensions 10 meters by 6.5 meters. All this water runs into a cylindrical tank with a base diameter of 4 meters. We need to find the rise in the water level. To solve this, we must first calculate the volume of water collected. We'll find the volume of the rain on the roof, convert it to the tank, and use the tank's dimensions to find the rise in height. Step 1 is to find the volume of water from the roof. The area of the roof is 10 times 6.5, which is 65 square meters. We must convert the rain depth to meters. 17.3 millimeters is 0.0173 meters. The volume of collected water is the roof area times the depth. 65 times 0.00173 gives a volume of 1.11245 cubic meters. Step 2 is to consider this volume in the tank. The volume added to the tank must be the same as the volume of water collected from the roof. The tank is a cylinder. Its base is a circle with a diameter of 4 meters, so the radius is 2 meters. The volume added to the tank can be expressed as PR squared H, where H is the rise in the water level. So 1.1245 cubic meters equals pi times 2 squared times H. Now we equate the two volumes and solve for H. We set 4 pi(h) equal to 1.124. Dividing both sides by 4 pi, we find H is approximately 0.0895 meters. The question asks for the rise in millimeters. To convert meters to millimeters, we multiply by 1,000. So, the water level rises by about 89.5 millimeters. This problem shows how volumes from different shapes can be linked. We've covered a wide range of topics today. Let's recap the key formulas we've encountered. For two-dimensional shapes, we have the area of a circle is par squared, and the area of a sector is a fraction of that, determined by the angle theta. The arc length is also a fraction of the circle's circumference. For three-dimensional solids of uniform cross-section, the volume is always the area of that cross-section times the length or height. And for other important solids, the volume of a sphere is 4/3 pi r cubed. The volume of a cone is 1/3 pi r squared h. And a very useful relationship is that the surface area of a sphere is equal to the curved surface area of the cylinder that contains it, 4 pi r squared. We also have formulas for the surface area of a cone and a cylinder. The key skills you need for IB are breaking down complex shapes into simpler components using the correct formulas and performing unit conversions accurately. Practice is crucial. To help you solidify your understanding, here are 5 IB-style practice questions. I will show you each question, and you can pause the video to attempt it yourself. Afterwards, I'll present the fully worked solution. Question 1. The minute hand of a clock is 8 centimeters long. Through what angle does it turn in 20 minutes? What is the area of the sector it covers in that time? Here's the solution. A full circle is 360 degrees and corresponds to 60 minutes. So, in 1 minute, the hand turns 6 degrees. In 20 minutes, it turns 20 times 6, which is 120 degrees. The area of the sector is theta over 360 times PR squared. Substituting 120 for theta and 8 for r, we get 120 over 360 times pi times 8 squared. This simplifies to 1/3 times 64 pi, which is 64 pi over 3, or approximately 67.0 square centimeters. Did you get the same answer? Question 2. A conical water fountain has a base radius of 2 meters and a height of 5 meters. Find its capacity in kiloliters. Pause the video to solve. Let's find the solution. First, we need to find the volume of the cone in cubic meters. The volume is 1/3 pi r squared h. With r equals 2 and h equals 5, we get 1/3 pi times 2 squared times 5. This is 20 pi over 3 cubic meters. Next, we convert this volume to capacity. Since 1 cubic meter is equal to 1 kiloliter, the capacity is also 20 pi over 3 kiloliters. If we approximate this to 1 decimal place, the capacity is about 20.9 kiloliters. Question 3. A solid metal object is made by placing a cone with radius 4 centimeters and slant height 9 centimeters on top of a hemisphere with the same radius. Calculate the total surface area of the resulting solid. Pause the video to solve. Here's the solution. The total surface area is the sum of the curved surface of the hemisphere and the curved surface of the cone. The circular base where they join is internal and not part of the surface. First, the curved surface area of the hemisphere. The total surface area of a sphere is 4 pi r squared, so the curved area of a hemisphere is 2 pi r squared. With r equals 4, this is 2 pi times 10, which is 32 pi. Second, the curved surface area of the cone. The formula is pi rs, with r equals 4 and s equals 9. This is pi times 4 times 9, which is 36 pi. The total surface area is the sum, 32 pi plus 36 pi, which equals 68 pi. Numerically, this is about 213.6 square centimeters. This problem tests your ability to correctly identify the surfaces that form the boundary of a composite solid. Question 4. An annular sector has an inner radius of 5 centimeters, an outer radius of 7 centimeters, and a central angle of 120 degrees. Find its perimeter and area. Here's the solution. First, the perimeter. It consists of the inner arc, the outer arc, and the 2 straight radial sides. We calculate the length of the inner arc using r equals 5 centimeters and theta equals 120 degrees. This gives us 10 pi over 3 centimeters. We do the same for the outer arc with r equals 7 centimeters, which gives 14 pi over 3 centimeters. The 2 straight sides are both 2 centimeters long. Adding them all up, the perimeter is 10 pi over 3 plus 14 pi over 3 plus 4, which is 24 pi over 3 plus 4. This simplifies to 8 pi plus 4, or approximately 29.1 cm. That's the distance around the entire shape. Now let's find the area. The area is the area of the large sector minus the area of the small sector. For the large sector, r equals 7, giving an area of 49 pi over 3. For the small sector, r equals 5, giving an area of 25 pi over 3. Subtracting these, we get 49 pi over 3 minus 25 pi over 3, which is 24 pi over 3. This simplifies to exactly 8 pi. So the area enclosed by the annular sector is approximately 25.1 square centimeters. Finally, question 5. A cylindrical storage tank has a volume of 10 kiloliters and a height of 3 meters. Find its radius to 2 decimal places. Pause the video to solve. Let's work through the solution. This problem requires a unit conversion before we can use our volume formula. The volume is given in kiloliters, but the height is in meters. We need to convert the volume to cubic meters. Since 1 KL is equivalent to 1 cubic meter, a volume of 10 KL is equal to 10 cubic meters. This is the crucial first step. The formula for the volume of a cylinder is V equals pi r squared h. We can rearrange this to solve for r squared. Now we substitute our values. R squared equals 10, divided by the quantity pi times 3. That's 10 over 3 pi. To find r, we take the square root of both sides. The radius r is the square root of 10 divided by 3 pi, which is approximately 1.03 meters. Rounding to 2 decimal places, the radius of the tank is 1.03 meters. This shows the importance of handling units correctly. We have now covered the core concepts of measurement, including circles, surface area, volume, and capacity. We've worked through examples of plane and curved solids, composite shapes, and practical problems involving conversions. These topics are fundamental to your IB Mathematics AI higher level course. The key to mastering these concepts is consistent practice and careful attention to detail, especially with formulas and units. Thank you for joining this DAR Tutors lesson. We hope you found it helpful.